You're in the Mass Effect track. This is recent Java exploitation trends and malware, presented by Matt O.
Yeah, thank you. So, can you hear me? Well, no? Hello? Looks like this one is not.
You're on. Okay,
Yeah.
talk.
Hi. Today, I'm going to talk about recent Java exploitation trends and the malwares. Let's talk about the background first. Actually, this very, very specific CVE, this one is very, very famous one, actually. The CVE 2012-0507. We found the first sample on March 2012. And this one was using a vulnerability, actually, that was patched at the time, just a few weeks ago. And somehow, this one was really, really popular with all those like malwares, the exploit kits. They were like using this like a lot. Like we are seeing millions of detections per month. And the thing is that many people think that they are now running Java on their system, right? But the truth is that Java is running more than 1.1 billion desktops in the world right now. So it's a huge number. So the other issue with Java is that Java is like a multi-platform. And the thing is that it is very, very easy to port just one Windows malware written in Java to Mac OS X or Linux. It is like really, really easy. So if you look at the source code down there, so it is from one of the malwares for Mac OS X. And you can see that they are just running some Unix command here. So Mac OS X is based on Unix. So they are using some CH mode. They are just changing some permission bits for some binaries they dropped. And after they are using launch.ctl. This one is the command line that is used in Mac OS X to launch any command. So they are just launching the dropped file. So just using like 5 lines, they just ported the whole malware to like a Mac OS X. This is so easy. So we can see that Java vulnerabilities has a kind of very, very like a mass effect. So let's see the timeline. Timeline is very, very interesting because even though the vulnerability was patched on February 2012, the first patch appeared on internet on September 2011. It's almost like 5 or 6 months ago before the actual official patch was released. So this one was not actually OpenJDK. So I believe the guy who maintaining this open source version of JDK or Java is kind of contributor to the whole project. So he accidentally just checked in his fix for this vulnerability. And it's been 6 months later, and Oracle finally patched the vulnerability from their official release of JDK and JRE. And just a few days later, a researcher who claims that actually claimed that he found the vulnerability in the first time, like even before September 2011, he posted a blog about that. And kind of interesting thing happening after that, like March 2012, the actual malware actually abusing that vulnerability appeared. So the blog post from that researcher actually didn't post the full exploit. He just posted a very, very basic proof of concept code. But somehow malware writers figured out how to use that for their exploitation and malware. And it was just a month later that we saw the Mac OS X malware abusing this same vulnerability. And the interesting thing is that at that point, Apple didn't fix their JRE yet. It's been 2 months later. They finally fixed their shipping version of JRE at the time. So there are a lot of chances to fix the issues. From the September 2011, they used the 6 months to fix it in official release. And after that, Apple used like 2 months to fix it their own like package of JRE. So it looks like the malware writers using this time gap between the information about the vulnerability and the actual patch and the actual updates from the users. They are using that time gap, and they are using these new vulnerabilities actively. The thing is that this vulnerability was never been 0-day actually. So this one is fixed by like Oracle already, but it is like a very, very effective way to like infect all those machines. So why this specific 2012-05-07 is so special? So that is one of the questions we will answer in this presentation. And the other issue is that many of those like Java malwares are using obfuscation. So you might wonder that I'm sure many guys will not be that familiar with Java like obfuscations. Because like if you think about obfuscation, maybe you can think about JavaScript obfuscation. But Java has their own obfuscation methods. So we will look into how we can like defeat that method. So before all this, we need to look into the Java security model. So Java platform security, they are like very, very strong actually. They have very, very solid model of security. So the first thing to note is Java code is loaded by ClassLoader always. This fact is very, very important actually because the first code loaded is always loaded by ClassLoader. And in the other word, if you have you have access to ClassLoader, you can load your own classes with your own permissions. So that is like not allowed actually, but you can use some vulnerabilities to use your own ClassLoader to make your own classes with any permissions you want. So we will explain it later. And the second important thing is that remote code that is downloaded from the internet, like Java Applet, actually they run inside the JVM sandbox. So the sandbox model has been in Java like a long, long time. So that is good. But the thing is that all these permissions are controlled by security policies. So they have the actual security policy file like this. So if you look at that, this one is just from one of those like default Java policy file from JRE7. And you can just open the file and you can see the default policies. So if you look at this part of the policy, looks like it's not permitting them much permissions. So if it is downloaded applet, it can't do many things. It is just running, and it is really, really restricted. So you can see that this security policy, ClassLoader, and the sandbox, three of them are very, very important elements in Java security. So they are actually very important in understanding the malwares. So security policy, I already explained it. It's about the permissions, about code that runs inside the JVM. So it's just defining what kind of resources they can access. So this one was the example. So if this one is one of the malware actually running, and even for the get-amp, if you look at the first line from this exception record, you can see the Java.lang runtime permission, and this one is category, so runtime permission category, and get-amp method is not allowed. Even this one is not allowed, just getting some environment variable, that is not allowed. So you can see that this one is kind of failed exploitation method. So looks like this Java sandbox is kind of very, very restricted environment. And the security manager is the actual object that is actually dealing with setting the security policies for the code. And there is actual classes there actually from the Java class, security manager class. So if you have access to this class, you can set the permissions for your own code or other code that will be run. But the thing is that you don't usually, if your code is from the remote code, if your code is downloaded from the internet, then usually you don't have any access to this method at all. So for example, this exception record. So the first step in exploiting like Java vulnerabilities, they usually call this method. Like from java.lang.System, they call setSecurityManager null. So it means that they are just nullifying security manager. So there will be no security at all. So this one is the first step in exploiting. So if you look at the exception record here, so it looks like it's using one of the old exploit, and actually it's failing. The exploit actually failed because I ran this malware using some recent runtime environment. So you can see that the exploit itself will try to run setSecurityManager null. So if you look at, analyze a lot of malwares, they usually, this one is the first step in exploiting. They just nullify security manager, and after that they do whatever they want to do. So if you look at these like exception records, then this is like a good sign of exploitation. There is no reason the just good code will call this. There are not many reasons for them to call this like setSecurityManager null. And the next very important concept in Java right now is actually type safety. So type safety, the name may be kind of very complicated to understand. Actually, it's very easy. It's about just type means data type, and safety means safety. So if you have some data type, like for example, if you programmed in C or C++, you have all those basic data types like integer, character, string. So if you write very, very weird program that prints out integers, you will print out really random memory area. So in that case, it is not type safe at all, right? Because you are supposed to be dumping out some like a string area, then memory region. But if you are just passing out some integer value, it will not work correctly. So that kind of thing is type safety. So just making sure one data type is not interpreted as other data types. So for example, integer to string, or string to integer, or that kind of thing. It should not be allowed. So for example, the type not only includes like integer, character, string, that kind of type, but they also include some kind of classes, unions, structures. They are all types. So if the code doesn't guarantee that one type is not treated as such type, it will make some problems. So there are two methods of actually verifying those type safety. So one is static type. So for example, if you write some C program that is printing out integer as a string, actually many compilers will complain about that because you are supposed to be passing some string pointer, but you are passing some integer. In that case, it will complain that. So it means that it didn't run the code, but it just did some kind of static analysis on those code. So in that case, it did some static type check. But for dynamic type check, so for all those objects in the memory, if they have some code that is checking the data types that the actual code is accessing, then that might be, you can call that as a dynamic type check. So whenever the call is made to the specific data type, then if it is checking whether it is making correct call, it will be dynamic type safety check. The thing is that if you do this like a routine every time, it will make a lot of like overhead. So usually for efficiency, for Java, they are mainly doing static type check. So the problem is that when they are doing static type check, if that static type check logic fails, it means that type safety will not be guaranteed. So one of those quotes here, type safety is the most essential element of Java security. That is from one of the book, like a Securing Java book. And this one is the kind of like a Bible for Java security. And it is kind of very old book, but it has like a lot of good information there. So they are saying type safety is the most essential element. So you might wonder, why is this so important? So I will explain it later. So let's talk about the vulnerabilities. So if you look at the vulnerable components, usually many parts are actually the runtime environment itself, the JRE itself. JRE contains a lot of libraries, components inside it. Historically, we saw deserialization scripting module, Java scripting module, and concurrency component. This one is 0507, and CORBA module. Those modules are known to have some problems before. And for plugins, so when you are talking about Java vulnerabilities, so many people talk about, maybe they talk about runtime environment, or they can talk about Java deployment toolkit or Java web start. But they are kind of like a little bit different like technology. So these are for like plugins actually. So they are not essential part of whole like a runtime environment. So if you just categorize all those like vulnerability types for Java, actually you can, overall you can see 4 different types. So the first one is type confusion. So this one is the vulnerability that is related to type safety that we just talked about. So type confusion means the situation where type safety is not working. So if type safety fails, it is type confusion. So why is this so important? Because as I said, the class loader, security manager, they are all like classes in Java, and they are object. So if you make some confusion, type confusion with class loader or security manager with other like a fake data type that the attacker made, then you can actually control the whole security model inside the JVM. So that's why this type safety is so important in like Java. So for type confusion, this is not a new concept. It's been known like more than 10 years. And if you look at this like a Securing Java book and this like Black Hat Asia presentation, it's been like 10 years. So it's been like talked about like a long time ago, but kind of it's forgotten. And it has a long story and a long history, and it is a kind of very, very well-known problem. So for example, for type confusion, there are 3 major vulnerabilities found recently. The first one is 2012-0507, the vulnerability we will talk about today. And the second one is 2011-3521. This one is the type confusion in CORBA module. So you can see that this one is from atomic reference array. The second one is from CORBA. So it looks like they are just happening in random like modules. So the vulnerability can happen from any modules inside JRE. And the third one is actually from hotspot field instructions. So when you are doing full field, get field instructions, and there can be some type confusion between static field and some instance field. So this one, 2012-17-23, this one was just found like just 3 weeks ago. So we are just looking into 12-05-07 and 12-17-23. Both of them, we are monitoring them. Actually, this one it is still getting more detections right now, but looks like this one, new vulnerabilities like catching up whole detections. So it looks like they are more and more like malware writers are like introducing new vulnerabilities. Second type of like Java vulnerabilities is logic error. So for example, when you are implementing some component for JRE, if you made some mistake, then it will lead to kind of like a vulnerability. So for example, 2011-3544, this one is vulnerability inside the Java Rhino script engine. So security manager is not implemented correctly. So you can, when you are calling, this module is for JavaScript execution inside Java environment. So when you are calling JavaScript, if you call like a security manager null code inside it, it will just nullify security manager itself, because the eval method from this script engine is kind of privileged code. So they forgot to like set the security policy correctly when they are running this security, what is that JavaScript code. And the second vulnerability is Java Web Start Basic Service Simple, this policy file, like overwrite vulnerability. This one is a little bit complicated because it involves with JNLP protocol, but basically you can overwrite the security policy file itself. You can just make the Java think that the provided policy file from your web server is the correct policy file for that applet, and you can set just all permission for that Java applet, then you can run anything you want. The third issue actually is memory corruption. So you might wonder, oh, there is no memory corruption for Java, and actually they exist. And for example, 2010 0842 and 2010 3552. So they are all memory corruption issues, some kind of traditional issues, but looks like they are not so popular. So somehow, right now, Java is not suffering much from memory corruption issues. They are much more suffering from type confusion issues right now. 2012, we have two major type confusion bugs, just as I explained. And the last type of vulnerabilities is argument injection. So this one is very popular with Java plugin, the plugin technologies like Java Web Start, Java Deployment Toolkit. So when you are calling those components, you can actually make it to pass some command line argument. So actually when the plugin is running, they will run java.exe or java.wexe or that kind of thing. And actually you can make to pass some command line argument, and you can make some command execution through that. So we can just call that argument injection. So you might wonder that if you are new to Java, malware world, maybe you can wonder, what kind of tool can I use? So we will explain it briefly here. So the note is that actually Microsoft doesn't endorse any tools that I'm going to explain. The tools are basically based on my personal experience. So for any researches, usually you have two methods. The first one is static analysis. The second one is dynamic analysis. So for static analysis, actually, first you have the compilers. They are much easier way to deal with some Java binaries actually. So for example, JD GUI or JAD, they are the most popular decompilers out there. And they are very effective actually. They can generate from the Java binary, actually you can create very nice decompiled source code. And sometimes you can just make it recompile again. So through that method, you can actually test the malware. And actually, sometimes JD GUI works fine, but sometimes JAD works fine, sometimes both of them fails. And there are always the possibility for them to fail, actually, because the malware writers use some kind of low-level manipulation of the bytecode, and it will make the decompiler a process to fail. So the compilers work just looking at some patterns that is generated by some a very popular Java compiling tools. So they are looking for that patterns. If they can't find that kind of patterns, then they will fail. So in that case, the next option is actually IDA. So you might wonder, oh, the IDA supported Java binaries. Yeah, they support it. And so if you are not so sure about the Java internals, the binary internals, you should use IDA to confirm your findings. So they show usually they show a good bytecode. Sometimes they also fail. So the next approach is dynamic analysis. So you can actually use debuggers. So there are some conditions actually. So you can use Eclipse or NetBeans. They are just a very popular Java IDE. But if you can decompile the malware itself, you can just decompile them as a source code form and just make them as a project and make it compilable. And the problem is that after you can the binary through the debugging process. You can put the breakpoint. You can inspect the like variables. You can actually watch how the malware is doing. So it is like a very, very convenient method. The problem is that if the malware code is not decompilable, then this option will not work. So the last option is actually instrumentation. So the thing is that for Java, instrumentation itself has a kind of long history, and it has been used for like all different kinds of like purposes. Mostly it was used for profiling, and there are like a lot of different purposes for instrumentation. But the thing is that you can use instrumentation for security research purpose. So you can just instrument the binary Java bytecode itself. You can put some debugging messages, and you can put whatever logic you want actually. So for instrumentation tools, you can use B-cell, ASM. Some people like ASM, some people like B-cell. So both of them are good actually. So now we talked about security model, and we talked about vulnerabilities and tools. Now let's look at the type confusion, because type confusion is the most prevalent like a vulnerability type right now. So this one, 2012-05-07, is the most like notorious one. So we are looking into that now. So this one is from the actual malware. So this one is detected as exploit Java. This one .b variant. So from our engine, Microsoft Security Essentials. So if you look at that, this is really simple code. So this is the main part of the exploitation. So the first step is like building some serialized object. So you might be very, very familiar with the serialized object if you worked with Java or C#, probably with C++. They all have serialized object concept. So if you have some object on the memory, so actually some object can be saved to the file or in byte array form. So actually these hex strings represent some object inside the memory. So it is just doing some string manipulation, and actually it's calling a read object method from this stream, and actually that one is object array. So, and actually they are referencing that object array 0 and 1 with this specific data type. So you might wonder what help type is. So actually help type is the type that the attacker defined. So you can see the help class later in the code. So atomic reference array, this is the type that is responsible for this vulnerability. So the type confusion happens when they are calling this local atomic reference array SAM method here. Actually, local atomic reference array is from here. So it's from the object itself. So it is calling one of the methods from the reference array and setting the index 0 to local class loader. So here is the class loader. So I told already that class loader is very, very important object in the JVM. So it's getting some class loader from the system, and it is passing it through this like method call. And actually during this time, type confusion is happening. So you might wonder what is happening there. So the thing is that if you look into the memory structure itself, so this whole square, this rectangle thing is actually the whole object that is read from the serialized object. So this one is array of object, and it has two members there. So this one is first member, index 0, and this one is index 1. And index 0 has its own array. So each help array, and the size is 1. And the first member is null. And array of object 1 is actually atomic reference array type. And this data type actually has private member array, and this type is actually object array. So actually this one is array is just doing referencing to this help object, help array. So if you look at this one is from the Eclipse debugging. So if you look into this, help 1 array, this one, the array member from atomic reference array is actually referencing to this like help one array. So if you look at this ID field, ID 90 here, and this one is ID 90, so they are same object actually. So this one, this structure, you can't make this structure using some Java code. You can't do that actually. So the attackers just manipulated the serialized object themselves. They know about the specification for the serialized object is open, so they just manipulated that structure itself. And after this call, like a local atomic reference array set object and set member from set 0 to local class loader, it means that this object, this array, you are just replacing the index 1 element to local class loader. So actually, this one is referencing to here. So it's just replacing the first member in help class. The thing is that if you look at this, the debugging thing, so you can see that the apply2, both of these and these are replaced with apply2 class loader. And actually, they are same because this is a reference. And the thing is that help array should contain help type there, but it's containing apply2 class loader type here. So this is type confusion. So type confusion is not kind of difficult concept. It is a really easy concept. So help array contains totally different data type inside it. So it's not, it should have a help type here, but it has some object that is not in help type. So this is the typical type confusion like a situation. And actually, so you might wonder that how can this be possible? If it is possible with just writing some code, you can just make like a Java modules very, very easily. But this is only possible when the vulnerability that is replacing some object without checking the data types exists in the trusted code. So the trusted code is like the code that is actually inside the JRE itself. So when the JRE, some of the part of JRE code is written in this way, not checking the data types when they are replacing some object, then it makes the vulnerability. So for example, for this code, we know that this set method from atomic reference array has the vulnerability, right? So if we call this atomic reference array set method with some index, and you can pass any data type here, actually you can replace the underlying object without type checking. And the fundamental reason why it is happening is that it is actually using Unsafe's put object volatile method inside there. So if you look at the code for that, actually it's very, very simple code. So you might wonder what unsafe is. So unsafe is kind of very, very unsafe method class actually. It's from the actually the JRE actually. So some MISC unsafe class, that is the class name actually. So they know when they made this class, this one is really unsafe. So this one is for some dynamic manipulation of Java memory and object. And it is kind of very, very low level, and it is unsafe as the name implies. But the thing is that this one is very, very efficient because it's just not doing any kind of type checks, anything. They are not doing anything. So this one is very, very efficient in like managing some manipulating memory. So this one is only allowed in trusted code, but somehow the trusted code itself, just I said, the atomic reference array class, just like that class, if that one has the vulnerability, then it will lead to like a kind of privilege escalation situation. So now let's look at how this type confusion can be used for exploitation. So we talked about help class. So you might wonder what help class is, but this one is just named from the manual writer. So help class is just happen to be there that the attacker chose. So help class is actually extended from ClassLoader. So if you look at the source code, it's like extension from the ClassLoader, and it has a public static method do work, and it's getting help class itself. So it is one of the methods from help class, and as the first parameter is getting help class. So this one is the actual flow that might be seen from bytecode verifier. So this one, the upper code is the actual exploitation part, the public class test. This one is subclass of applet. It means that this code will be run first from whole like a binary. And this one, ClassLoader, help class, this one is extending ClassLoader itself. So if you look at this, in this part, actually, it's just reading the object, and it's just assigning, referencing this array of object 0 with help array. They are help array type, just as we saw. So it's just passing help of array of help index 0, and that should be help type, right? So it's passing and do work, it's calling do work here, and the control flow goes here, do work. It's getting help type. And do work is accepting help type. So there is nothing wrong. So do work is accepting help type, and the code here, help do work is just passing help type. And that's it. The verifier from JVM just thinks that, oh, everything is just fine. And they just let the code run. So from this static analysis from the verifier, they don't see that the actual atomic reference array set method will change the underlying object type. So if you do some kind of dynamic analysis, so array of help is help array type. This one is same as static analysis. But when this call is made, the type confusion happens. Actually, array of help 0 is the applet2 class, which is a subclass of ClassLoader type. And after that, it's passing that help type object with ClassLoader actual object. So underlying object is subclass of ClassLoader, but like a bytecode level, they think that this one is still help type. So it is type confusion as the name implies. So this one, do work is expecting help type, but it thinks that, oh, it got help type, but actually it got ClassLoader type. And it's calling some defineClass method from this help type, which is a subclass of ClassLoader, and it's just creating some class. defineClass is a method from ClassLoader, and which actually can set up some, create some class with your own permission. So it's passing some local protection domain. Actually, you can specify the permission that actual code inside in the byte array will have. So if you pass some like all permission here, the code will have all permission. You can do whatever you can do. You can execute programs, you can delete file, you can create file, you can do whatever you can do. So next thing is that it's calling new instance. So it's just instantiate the class itself. So you can see that from the static analysis point of view, you can see the actual underlying operations from the trusted code. And it will not see that this local atomic reference array set method will make some type confusion. And it thinks that everything is fine, and it will just pass some type confused variables. So you might wonder, the next important thing is that the next very important concept in exploiting Java vulnerabilities is actually defineClass method. They are kind of very protected from abusing. So this method has kind of some history being abused in the past. So kind of, if you call this method with some protection domain, so if you look at this, it's setting some URL, file URL. So it means that the class is loaded from local file system, and certificate is kind of null, and it's setting the permission here, and it's setting all permission here, and it's creating the protection domain here, local protection domain, and it's passing this local protection domain to defineClass method. So the thing is that you can't access defineClass method outside from ClassLoader itself or subclass of that ClassLoader. So you should subclass ClassLoader itself to call define class. So you should make some subclass just like to call this define class method. You should be doing this. Just extend ClassLoader and you create your own help class, any class, and you can call define class in that case. So you might don't know what is wrong with this picture. So you are extending the help class here, and you are calling the define class. If you have this class, you can do whatever you can do, right? But the thing is that even though you have that help class, you can't, let me see, you can't instantiate that class. So you need this createClassLoader permission to instantiate any subclass of ClassLoader. So even though you can create the ClassLoader, your own class that calls define class, you have it in your code, you can't use it. So it's useless. But the thing is that the type confusion thing, you are using this type confusion. So if you pass some already instantiated ClassLoader here, it will be, this code will make define class to be like a code. So you are just passing. So if you go back to the code, so it's up there. So if you look at this code, actually it's just getting the ClassLoader, the system ClassLoader. It's getting get ClassLoader, and this one is ClassLoader. It's just doing the type confusion. And actually you are calling the define class method from this instance. But if you are just calling local ClassLoader define method here, you can't do that because define class method itself is kind of protected. So that's what is happening with this type confusion thing. So you can see that this type confusion is usually used in like this form. You are just subclass, just extend a class from ClassLoader and create some static method here, and you just call the define class method. This is really, really typical method in exploiting Java vulnerabilities. So in summary, you can see that using like this type confusion. If you don't have any type confusion, you can't do anything like instantiate ClassLoader from any class extended from ClassLoader, and you can't access a define class method from outside of the code, even though you have the instance of that ClassLoader. And what you can do is help class is extended from ClassLoader, and it has access to its own like inherited define class method. And using this type confusion method, you are just passing instance of instance of the ClassLoader, and you just make the call from that. So the next subject, so we talked about tools and vulnerabilities and the type confusion itself. We are talking about obfuscation. So this one is for malware analysis actually. So the obfuscation is about the making malware like inform more of like not understandable from the human side. So they are usually using some language features. So for example, for JavaScript, they are using eval function and document write. This one is like very well known. And for ActionScript in Adobe Flash, they are using Flash display loaders load bytes, and they are loading some sweep file itself in dynamic way. And for Java, they are using these two classes, Java.lang class and Java.lang.Reflect.Method class. So usually they are using the method here, like from Java.lang class, they are using for name. So using this method, actually you can look up the class using the name. And using this method, get method, you can actually look up the method itself. And new instance, you can use this method to instantiate the class itself. And this method, like class, is actually returned from get method. And from there, you can use invoke method to invoke the method itself. So you just look up the class first, and look up the method, and instantiate the class itself, and after that you invoke the method itself. So in this way, the code that is like running some specific method from a class will not appear in the code, the bytecode itself. So you should run the code to see what they are doing. So for example, this one is from the actual malware that is exploiting 0507. So this part is about like a class resolution. The first argument, param object 1, this one is actually the class name. So they are passing the class name, and it is passed to here. And actually they are calling class for name to look up the class, and they are just returning it. And after that, it's calling get method, and it's passing the param object 2, which is method name. And it's passing param array of class, and it's actually calling the method itself. So using this one line, they are actually calling any method they want. So they are just passing the parameter types and parameter objects here. So for example, they are doing like this. So this LBLA is the call here. So this one is from class LB and the method LA. So it's calling LBLA here. It's passing all those parameters and class names here. So for example, the thing is that these strings are all like obfuscated. So for example, this one, local NLY, this one is supposed to be class name. So let's trace where it is coming from. So for example, this class local LY class name is actually from the other class. So this one is bytecode representation of how this assigning is happening. Actually, if you use decompiling, this part is not decompiled, because these parts are very important in obfuscation. The malware writers do some kind of a low-level manipulation so that we can't decompile the code. So you should look into this using IDA. And it sees that these are the old JVM instructions. It's loading the register 0 on the stack, and it's calling some static method here. And it's accessing a static field there. And by push is just pushing 15, number 15 loading, and actually you can just represent it as this one. So it's N, LY, it is assigned from NG15 array member. So N is the class name, LY is the variable name, G is the array name. So we need to trace G15 here. So G15 is actually coming from here. So it's loading, LDC is just loading this string to the stack, and after that it's calling this method, MET001-213, this subroutine. So it's just pushing this string and just calling this routine. So let's look at this routine. And after calling this routine, it's assigning the value to this NG15. So it's easy. So this one is the actual de-obfuscation routine. So you can actually use IDA to see this graph. So the first basic block is actually doing some kind of switch statement actually. So it's using IRM operation that divide the array index with 5, and it's doing some switch, and it's going to 1 to 5 different branches. And if you look at the branches, they are very simple. They are just pushing some variables here, some constant numbers. So if you express this as a pseudocode, actually, you can see that for I0 to string length, it's just divide I with 5 and using the remaining value as the switch. And for each case, it's using different XOR key. So this is very simple de-obfuscation. So after that, it's just doing some XOR here, I XOR and it's just storing them back to the array. So each decoded value is like original value XOR and XOR key. And the XOR key changes every time. Like there are 4 different XOR keys. So for example, this original obfuscated string is decoded as Java.lang integer if you follow this same algorithm. So it's a really simple algorithm. The thing is that these keys here, every keys, I talked about 5 different keys. The value changes every time. So whenever we have new malware, they are using different key. So in that case, you can't automate the process. You have this string, but you are not so sure what kind of keys they will use. So some kind of human intervention is needed. So we need some kind of automation here. So this one is the last chapter of this presentation. So we use instrumentation in this case. So as we just talked about, instrumentation is like a very, very stable technology in Java. So you can use dynamic analysis on Java bytecode. And just like this one is, the actual code is more complicated than this, but this one is just showing very, very like a simplified version of the instrumentation. So for example, we talked about the java.lang.Reflect.Method classes invoke method. And we can just replace that method with our own hook. Like we created our own package, inspector package, and our own like a ClassHook class. And we created our own like invoke method here. And we just made it to call our own like invoke hook instead of their own like a system method invoke. So we can actually monitor every invoke method that is called inside malware. So if you look at the inspector package, this code is totally written by us. And inspector package, ClassHook class, and inside it has invoke hook. So the method, object, the parameters, they will be passed to our code. So we are just printing out some debugging messages. We just dump out some objects or whatever. And after that, we are just calling the original method. So this is the basic way of like using instrumentation for the malware research. So after that, if you run this instrumented binary through the actual like JRE environment, then you can get Java log if you enable the Java log from the control panel, and you can get the messages like this. So this one is for 2012-0507, and you can see that it's calling actually the previous obfuscate code is actually calling atomic reference array set. And this method and argument, the first argument is 0, and the second argument is apply2ClassLoader. So you can just determine the vulnerability using this automation process. So that is what we are presenting here. And the conclusion is that there are like different kinds of like vulnerabilities for Java, but currently type confusion vulnerability is the most prevalent one. And we see that the malwares are using like 0507 and 1723 actively right now. So you must update check your JRE version. If you are working for a company, you should check that. And if you are at home, you should check your JRE version and you should update them. So because JRE doesn't update automatically. It shows the notification like what is a balloon, but you should do the manual update. Or you can just disable the JRE from the control panel. So you can go to control panel and select the Java from there. And there are some menus like a Java tab, and you can click the View tab, and you can actually disable some specific JRE versions. Or you can just uninstall the JRE if you don't use JRE at all. So that is the most safe way. And as you look from this like presentation, if you write the exploit in right way, and if you are not patched, the success rate for exploitation is like 100%. So this one is really, really dangerous, and you should be doing something like update, remove, or like disable. So the next thing is that Instrumentation can be used for automatic analysis of this, like Java-related vulnerabilities and malwares. And finally, thanks to Chun-Fing from Microsoft Malware Protection Center, he helped with the CVE 2012-0507, and thanks to him. And that's it. Any questions? Yeah, thank you.